Hello all. Let us solve few examples of groups. The first question here is, show that the set of all positive rational numbers Q plus forms an abelian group under the composition defined by A star B is equal to A into B upon 2. So here we are dealing with positive rational numbers, and the operation under consideration is A star B is equal to A into B upon 2. So if we take any two rational numbers A and B and perform A star B, it means multiply A and B. So product of rational numbers is a rational number, and half of that is again a rational number. So this is going to be positive rational number. So it belongs to Q plus. Positive into positive is a positive. So it belongs to Q plus. So the operation is binary in Q plus. Next thing, because the star depends on ordinary multiplication, it will be associative. Let us see. Let us deal with LHS equal to bracket A star B bracket close star C. Clearly A, B and C are all members of Q plus, means they are positive rational numbers. This is equal to, first we are to perform A star B. So the value is going to be A into B upon 2. We multiplied them together and half of that star C. So this will be AB upon 2 as it is, and so let us continue here. This is A, okay, and A into B by 2, and now outside we multiply this by C and half of that. So let me write this half over here. Now multiplication being associative in usual sense, I can say this is equal to, let me put this half as it is, and I can say this A out into BC, and upon 2 let us add this there itself. So what happens is, this is equal to half A as it is, and the bracket you can see is nothing but B star C according to the definition of star. And further I can write this as A star, whatever is in the bracket. So we can see this is what is our RHS. So LHS is equal to RHS. What we have observed, star is associative. Star is associative. So we witnessed two conditions. One was the binariness and the second was associativity of the operation. Next comes is the existence of identity. We want a positive rational which when multiplied to A, we get back A. So let us write in our notations. So suppose E is the identity. So A star E must be equal to A. This is what we require. So take 2 seconds to think of. So hope you are guessing correctly. What we get is A into E ordinary multiplication divided by 2, and right side we want it to be A. So by usual multiplication, what we get is A into E is equal to twice A. A is a positive rational, so I can divide both sides by A, and what we are left with is E is equal to 2. So 2 being positive rational, it belongs to Q plus. So identity of this operation star is present in Q plus. It belongs to Q plus. The next thing comes is the existence of this inverse with respect to star. So let us try to find out the inverse. For any A in Q plus, suppose A star B happens to be E. Now A star B means A into B upon 2, and the value of E we have found out, it is 2. Therefore, the value of B will be 4 upon A, and as we know, A is positive, rational, so 4 upon A is also a positive rational, so it belongs to Q plus. It belongs to Q plus. So inverse of A will be 4 upon A, and for every positive rational 4 upon A will always exist. So all the 4 conditions hold, and therefore our Q plus with the given operation is a group. The set of all positive rationals with star defined as multiply the numbers and half of it, that is itself a group, and A star B will be equal to B star A because it depends on usual multiplication. So as it depends on usual multiplication, A star B is A into B by 2. We know 2 4s are and 4 2s are one and the same thing. 3 5s are and 5 3s are one and the same thing. 11 7s are and 7 11s are one and the same thing. So I can write this as B into A by 2 because it is ordinary multiplication and half of that, and which I can further write as B star A. So star is commutative, and therefore the given set Q plus along with the star is an abelian group. So if the thing is required to prove, you need to show binariness, associativity, existence of identity, existence of inverse, and at the same time commutativity is also to be shown. Then and then only we can claim that it is an abelian group. Now let us deal with another example. The question says, for a fixed point ordered per AB in R2, define T A comma B from R2 to R2 by xy goes to ordered per x plus A comma y plus B, means we are adding A to the x coordinate and B to the y coordinate. So then show that G, the set of all TABs where A and B are real numbers, is an abelian group under the operation of composition of functions. So here we have to deal with the fact that ordered pair AB means A and B are both real numbers. The operation depends on the suffix AB. When I say, I would like to explain this too. When I say T5, 7 from R2 to R2, this will mean the image of xy, ordered pair xy, under this T57. I forgot to write 57 at the base, so let me adjust here. Okay, T57 of xy will be equal to the ordered pair x plus 5 as the first coordinate and y plus 7 as the second coordinate. This is what I mean by this particular operation. If I go for t, it can be negative also. So if I deal with minus 1, 2, then t of minus 1, 2 of ordered pair AB will go to ordered pair A minus 1, B plus 2. So what we want to point out here is this T, A, B. This A and B play role while defining the operation. Ordered pair xy goes to, the image of ordered pair xy becomes x plus the first number and second place will be y plus the second number. This is what we have. Now we are dealing with a set of functions. G is the set of functions defined in this manner, and they are asking you to use the operation of composition of functions. What is meant by composition of functions? So if I at all have two functions f and g, if suppose I am handling functions f and g, f from suppose R to R and g also from R to R, then G circle f, this is composition of two functions. When operated on x, what will be the output? Output will be G operated on f operated on x. So this means we are talking about G of f of x. This will be G of f of x. So let us see what happens in our case. So we are dealing with the composition of functions. So very first we have to check whether this operation is a binary operation or not. The operation of composition, will it be binary or not? So this was just the demo of how the function works. So I would like to erase it. I won't keep it here. Alright. Now what the function says, for a fixed point AB you define this way. So you may have another point CD also. So you are having T, A, B from R2 to R2, and another function from the same set G, we may have T suffix C, D from R2 to R2. Now we want to take the composition of these functions. So T, A, B, circle T, C, D. We want to see whether it belongs back or not. So I have to operate it on some ordered pair xy. So by the definition of composition, outermost function operates on the inner one. So TAB will be outside, operated on T suffix CD, operating on x, y. Now what will be the output? this will be equal to t suffix a comma b of. Now what is the output here? Output is x plus c as my first coordinate, comma y plus d as the second coordinate. So certainly this will be equal to, this will be equal to ordered pair. X plus c was there already. X plus c and plus a. This is our first coordinate. And second coordinate will be y plus d plus b. So what we have got is, again pattern is the same. T suffix c plus a, comma d plus b. Operated on ordered pair xy. So what this means? The function t suffix c plus a, comma d plus b will belong to the set G. It is of the same pattern, so it belongs to G, and therefore what I can say, my function of composition is binary. Function of composition is binary. One more thing, because it depends on addition, we can very easily show that addition being associative, this composition of functions is associative. Third thing, we want to find out what will be the identity of this particular. So let us go for identity. T suffix a comma b, composition with something should give back t suffix ab to me. So for the time being, let us call it as t suffix u comma v. We want to find out the values of u and v if they exist. What we mean is, the composition of t suffix a comma b with t suffix u comma v must be back t suffix a comma b. So unless we operate by this, we can't decide. So let us operate t suffix a comma b composition with t suffix u comma v operated on ordered pair xy must be equal to t suffix ab operated on x comma y. So what this gives us? This becomes, as we have already done, so it will be ordered pair x plus u plus a, comma y plus v plus b, which is equal to x plus a comma y plus b. And now if we equate the corresponding coordinates, the result is u must be 0 and b also must be 0. So the identity for this particular operation, will be certainly t suffix 0 comma 0. This will be the identity. This is usual. 0 plays the role of usual identity for addition. Same way, If I go for the additive inverse, what I will get? For A, the additive inverse is minus A. So for T suffix A comma B, the additive inverse, I mean the inverse will be T suffix minus A comma minus B. We can verify this. So what this has given us? The set G along with this particular operation becomes a group. Now the thing comes to whether it is commutative group. So basically this composition depends on addition only, and addition is commutative. So this particular is also a commutative operation, and that is why it is an abelian group. So once we can verify it by doing it ourselves. Thank you.